Good afternoon, everyone. This is Bill McShane from the Water Power Technology Office. We are here for our Innovating Distributed Embedded Energy Prize Phase 3 TPL level assessment presentation. This is like the senior course in TPL. We've had Phase 1, or like the freshman course, during Phase 1 of the prize, and then we had a second course in the second phase of the prize. And I'm pleased to bring you this one as well, to sort of give you the intro. Next slide, please. So just to level set everyone, this is the InDEEP prize is a $2.3 million total prize pool. It's split over 3 different phases over 2 years. We made 15 awards in Phase 2. I think we made 19 awards in Phase 1. We're trying to incentivize progress in early stage research, among several other goals that are in the rules document. And we really need your help to solve technical challenges that could be applied to wave energy. Next slide, please. So here are our prize goals: leverage WEC innovation to systematically develop DEC tech concepts. We just had a presentation on DEC tech, distributed embedded energy converters, build a solver community, encourage development of novel DEC tech designs with high potential, and refine our WEC innovation methods. And again, these are all in the rules documents. You guys know where they're at. So go on to the next slide, please. I feel like we're missing an introduction slide. Okay, leaderboard scoring. We do have leaderboard in Phase 3. You will get points since you're attending this today, and we're very glad you do. If you ever have any questions, you can look in the rules document. You can put a note in the forum in the HeroX page as well. And the score, the points to contribute to your final score. Is there a next slide? We might be missing the little intro. All right, well, I'll just say the video is being recorded, and please make use of the Q&A tool and the chat tool at the bottom when we open up for Q&A. And with that, I'll hand it off. I hope I didn't go one slide too many. So with that, I'll hand it off. Thanks, everyone, for attending.
Hi, everyone. I'm Dr. Nicole Mendoza, and I work here at NREL on the WaveSpark team. And so I will be introducing our guest presenter today, Mr. Jonathan Colby, who is the president and founder of Streamwise Development. He is an independent consultant in the wave and current energy converter space. He is extremely active on the international community, particularly in terms of standards development. And he is the chair of the IEC Technical Committee 114, which works on international standards for marine energy conversion systems. And he also convenes the Marine Energy Sector Working Group, in particular working with IECRE, various testing certification bodies, and independent wave energy converter companies. Before that, he was 15 years at Verdant Power, which is a current energy converter company. And he has a wealth of knowledge and experience in the space. Next slide, please.
Thanks for the kind introduction, Nicole. Happy to be with you all today.
Thank you so much, Jonathan. We are very grateful that you were able to spare time to join us today and speak on this very important topic. Okay, so today we're going to tell y'all about the Technology Performance Level Assessment, which provides a holistic measurement or assessment of a technology's potential, which is measured and defined by all the different considerations that one needs to have when the technology is commercially ready. We will talk about specifically the submission requirements related to TPL for this prize, talk about a couple of topics as well as the individual questions, any changes from Phase 2. We'll give a broader overview of TPL tools and methodologies, and also briefly talk about TPL as a service as provided through the POET-sponsored and WPTO-sponsored TEAMER program. We will conclude and wrap up with reminding y'all about the various types of competitor support mechanisms, and then open it up for Q&A. Next slide, please, and thank you all very much.
Hello, thank you very much, Nicole. My name is Jochen Weber. I wanted to say a few words about the background of technology performance levels. The motivation to develop these came out of the clear observation, no news, that technology development of wave energy is a challenging task. The main observations are it's expensive, takes a long time, there's a high risk involved in it, and there's often a kind of a confinement to a small IP space due to the nature of how companies need to run and get their investment. So in order to alleviate that, and with the knowledge that technology readiness levels were around for a long time, they were partly followed, sometimes steps were skipped. And one major consideration of how promising the technology is, I believe, was not considered to the same degree on how ready a technology is. So how mature it is or how good is it? So that's why we consider developing those technology performance levels. Next slide, please. The very high level simple definitions, kind of an analogy to the definitions of technology readiness levels, which are sometimes just boiled down to one sentence or a little bit more refined. So an analogy to this, also nine levels were chosen, and the three categories, low, medium, high. And at the very rough understanding of these three main categories, one could say that low, there's fundamental, maybe conceptually inherent challenges in the technology that it may not be possible to bring it to a high-performing technology once it's a product, because they are even at the conceptual fundamental level. In medium, let's roughly say there are things that are promising and other things that may need to be improved and fixed. And high is classified as technologies that are economically viable and competitive as a renewable energy form. So what does that mean? In the original definitions, we said, okay, the market entry is probably in this high level. They must be economically viable or become economically viable while in commercial operation. So 7 could be understood as competitive with other renewable energy sources, given favorable support mechanisms. That would have been something like years ago, the tariffs that were used in solar power to bring up the production and bring the prices down. 8 would be sustainable support mechanisms. So it's competitive in a setting like this. And 9 would be the technology is simply competitive without any support mechanisms, and not only competitive renewable energy, but also competitive with all other energy, which in nowadays is the same thing, because renewables are the cheapest form of energy. So these were the early definitions, and this is much more refined and grounded on much more detailed metrics or much more detailed cost and performance drivers. And with that, we come to the next slide. Thank you. So cost and performance drivers. The most apparent and clear metric for economical viability is clearly levelized cost of energy of a technology that's developed to a high degree, or an estimation of that at earlier technology development stages. And the characteristics of levelized cost of energy is that everything is in currency units, of course. So maintenance or capital expenditure or a replacement of components and the financing itself, of course, to have the levelized in there, is all in dollars. So when these dollar numbers are not available, estimations must be made. At the same time, one thing is clear, there's an undisputable formula for LCOE that's utterly objective and undisputable. Now, when we go into other cost and performance driver considerations, they could be very inclusive, like levelized cost of energy is, and like CapEx, for example, is, or they could be very fundamental. They could be something like redundancy, which, what is the unit for that? So the question came up, what kind of characteristics should a selection of these capabilities have? because they could be all over the place. They could be very close to LCOE. There could be a dollar amount for the main subsystem, but there could be another aspect in there, which is maintainability. And so in order to sort out a certain consistency in those choices, following, design requirements for choosing metric systems are being made. Next slide, please. So when we look at those that we have here in the middle, it's supposed to symbolize that the funnel is completely covered from bottom from top to bottom, meaning it should be complete. There shouldn't be any aspect missing. I think that's clearly fundamental. Then in terms of right and left, there should be equally either high level and generalized or precise on the dollar amounts. So either very much on the LCOE side or more cost and performer driven side. And they shouldn't be overlapping. That would mean we're double accounting for certain aspects. So there are choices like that in the middle here, and IEA, OES, and different publications and international efforts have led to suggestions of such capabilities to be considered to assess performance metrics. And the choices for TPL were made to say, hey, we want to include everything that can influence cost and performance. And our premise is about holistic everything, and we're not excluding anything that we can't deal with, to put it that extreme. So we want to make sure that we are not even forgetting any known unknowns, even if we don't know what to do with them, but we have to consider them. And in that process, we also want to identify unknown unknowns and make them known unknowns so we can deal with them. So this diagram is supposed to show that on the left-hand side, the choices that were made for TPL are, we want to include everything, even if we don't know how to deal with it, because we're at least trying how to deal with it. And even if we don't really know how they all come together, because that would be a very magical hyper simulation of marine operation of a tire farm, plus all the physics that would support a precise identification of the cost and performance of the entire system. So this is attempted to be symbolized with all these arrows, which are clearly a small subset. So the cost and performance drivers of TPL in many, many multi-dependent ways would influence another set of capabilities, which would influence the final levelized cost of energy. So that's all to this slide. Next slide, please. Okay, now once we have these two different systems, the technology readiness levels, which are expressing how far is the technology under development to being a purchasable product, or to be entering mass production to have products available. So that's going from left to right. And the technology performance level are an independent dimension of this, because it's asking what is the promise of a technology under development to become a techno-economically viable technology. So once I reach TRL 9, where will I be with my promise to be economically viable? Meaning also, will I be in a situation where I can enter a market or even ignite a market? And once we have these two dimensions, we can ask ourselves, these are two independent variables, so it's a two-dimensional space. We can ask ourselves, what is the best way on how to move around this plane to arrive at market entry? And the best way is identified by the lowest amount of money, the lowest time for development, and the lowest risk, as far as we can identify that and as far as is possible. Yeah, so having the technology performance levels opens up a much greater perspective on what choices we can make and should make when we develop a technology. And this is what we have tried to bring into this prize as well, in a very reduced and very adapted form. So I hand it on to the next speaker. Thank you. Next slide. Yeah.
All right. Thank you, Joachim, and thank you all for attending this morning. I'm Thomas Mathai. I'm with the National Renewable Energy Lab. And I'm going to start by reminding you of the phase 3 submission requirements. There are 6 items as shown on this slide, and TPL is one of the 6. As usual, we have posted the phase 3 TPL template on HeroX. So please download it, fill that one in, and submit by the phase 3 deadline. Next slide, please. This is the question format, which you are already familiar with, so I won't dwell on this. So let's move on to the next one. This slide is again to remind you where these questions come from. We have a systems engineering study for the full wave energy farm, and this prize is only concerned about wave energy conversion. So it's a small subset of the big systems engineering. Nonetheless, every question that we have posed can be traced to a capability in the overall capabilities hierarchy. Next slide, please. Okay, so starting with this, I have 13 slides covering the topics the TPL questions pertain to, but many of these slides are the same as what I presented in phase 2, so I will not dwell on them, simply skip over them and focus only on the new slides. This first slide is a new one, and it's about metamaterial. Now, the term metamaterial usually means engineering the geometry to yield properties or material parameters that are different from natural properties of materials, usually done to manipulate the way the material interacts with the field, like electromagnetic field, and usually involves arrangements of geometric structures whose size and spacing are much smaller relative to the scale of the spatial variation of the exciting field. But here, when we talk of a deck-tech metamaterial, we are talking about any arrangement, homogeneous or heterogeneous, of decks, which structurally connects individual decks and provides mechanisms for energy transfer between them, such as electrical or fluidic conductors. And in phase 3, we are asking you to answer all the TPL questions from the perspective of the deck-tech metamaterial instead of an individual deck. And that is really the main difference from phase 2. Next slide, please. Now, there's a question about whether your deck-tech metamaterial can also act as an actuator. Now, the primary function of the deck-tech metamaterial must be to act as a framework for energy conversion. But the capability to act as an actuator may be a nice-to-have feature, but you won't be penalized if your deck-tech metamaterial cannot act as an actuator. We just want you to think of being able to act as an actuator as a potential as a useful capability. Next slide, please. Now, this one is about design loads, and it's the same as in phase 2, so I will just skip it and go to the next one. And this is about measures of merit, like efficiency, energy density, and power density, and we've discussed this in phase 2, so I will skip this also and move to the next one. Okay, so I have put this diagram here to talk a bit about the energy flow in a VEC. When you put a wave energy converter in a wave field, the waves act on it, or in other words, the waves do work on the VEC, and some of this energy is radiated back into the sea by the VEC, and the remaining energy is captured. And this energy capture is shown by the dashed box on the left. And once this energy is captured, it is converted into a useful form like electricity, and that conversion is shown by the dashed box on the right. Your deck-tech metamaterial must play a useful role in the conversion. So the net efficiencies we ask you about in the TPL is the efficiency of this conversion, and it's nothing to do with the energy capture. So that's the point I wanted to make here. Next slide, please. This is about materials, and this is the same as before, so I will move to the next one. And this is manufacturing. Also, we have gone through this last time, so I will skip this too and go to the next one. Okay, so here on the left, if you look at the red bar chart on the left, I've shown estimated failure rates of conventional WEC subsystems, with the caveat that these are not actual failure rates. These are failure rates of similar components in different environments, but then suitably extrapolated to a WEC environment. But for the moment, assuming these failure rates are representative, you notice that the PTO has the highest failure rate. And mind you, these are conventional PTOs, and which represent single points of failure. And the next worst offender is auxiliary systems, which includes data acquisition and control. And the next worst offender is the structure, which includes mooring lines. Now, all these failure rates are way too high and definitely poses a hindrance to economic viability. Now, if you look at the red bar chart on the right-hand side, I'm showing the failure rates of wind turbine components. And this is not an apples to apples comparison, since they are not the same subsystems that we are talking about for WECs and wind turbines. They are not even subsystems at the same level of detail. So it's not a good comparison. Nonetheless, clearly wind turbines have managed to achieve very low failure rates. And moreover, in the case of the more frequently occurring failures, they managed to keep the downtime following a failure to just a day or two. This is shown by that blue bar chart on the right. So higher failure rates are sort of balanced out by short downtimes. And I assume they achieve this by having service teams who can respond to these events very rapidly. But this is something very difficult to do for wave energy converters because we have a very hostile environment to deal with. Next slide, please. This is a pictorial representation of the Beaufort scale, which is commonly used to designate the severity of sea states. So on the top left is flat, calm seas. And then as you traverse each row, the sea state gets worse and worse. And the first picture in the second row is Beaufort scale 4, which is 1.5 meter seas. At anything beyond this, virtually all kinds of marine operations like device retrieval or personal transfer are very difficult and practically impossible. So if you want to access your device, you are forced to wait for favorable weather windows or periods of sustained calm weather, and this adds to cost and adversely impacts availability. Now, next slide, please. And now all this to say that reliability improvements are crucial to WECs. And this is an area we think the deck tech can shine because redundancy is inherently built in, almost by definition. And it is sort of like the Christmas lights, you know. Even if some lights fail, there's no single point of failure. So all the remaining lights work. So you can still put it on your Christmas tree every year. Next slide. This is about safety. There's nothing new here. It's the same as phase 2. So we'll move to the next one. There are questions about external power input. Again, nothing has changed. Next slide, please. And these are some principles that you can, that helps you, that enhances recycling and reuse. Again, nothing has changed here. So let's move to the next one. All right. So finally, on this slide, I have tried to put TPL in the context of the various design and innovation frameworks we have referenced in this prize. These frameworks often have the notion of an ideal system, which is shown in the top right box. But they all have different philosophies and different approaches to getting there. For example, Tris in the blue thought bubble wants you to resolve engineering contradictions in a win-win way without compromising. And it gives you a framework for formulating contradictions and then points you to a finite search space of potential solutions, which you then have to check one by one. Axiomatic design in the green bubble gives you two rules. Number one is to maintain the independence of the functional elements. And rule number two is minimize the information content, which the way I understand is a complicated way of saying reduce coupling between your subsystems. Design thinking in gray wants you to look for the intersection of desirability, viability, and feasibility. Now, TPL also points you in the same general direction. It makes you aware of which rung of the ladder you are and nudges you up. But its objective is not to take you to an ideal system, but to take you to techno-economic viability in a given market. So what you have seen in the price is a very short version, as Jakob mentioned, of TPL customized just for this price. But now to give you a quick overview of the smorgasbord of TPL tools and methodologies we have developed under WaveSpark, I pass to our guest speaker, Jonathan Colby. Thank you.
Yeah, thank you, Thomas. I would like to note that there's a question in the chat for you on slide 22. So I don't know, do you want to do that now or do you prefer to do that at the end of the webinar?
I will look at it. I'll do it at the end.
Very good. Very good. Well, greetings, everyone. Again, my name is Jonathan Colby. I'm very pleased to be with you today. I've been in the marine energy industry coming up on 19 years. And I've been intimately involved over the last few years working with the team at NREL and Sandia on the TPL tool. And so you've heard a number of the details and the justification for why we have this tool. And so I wanted to move out a little bit, if you will, to a larger vision. And the first thing we want to share is that the tool itself has undergone a long evolution to what we now call the version 6 of the tool, which is available online. And so initially the versions 1 through 4 were based on an Excel spreadsheet type derivation. And this evolution through versions 1 through 4 can be seen sort of graphically here. Version 5 was integrated into a Python framework. And most recently, version 6, not quite yet, apologies. Version 6 is now available online. The website is shown there. There is a spreadsheet available for version 6 for those that are interested. But for this particular version, what we're focusing on is the Wave Energy Converter Continental Grid application. And I think one of the key points is that through the version 1 through 6, has been this continuous assimilation of feedback that led to the improvement of the tool, further development, and the release of subsequent versions, again, now leading to version 6. And so sort of just want to reiterate that your feedback is really important, and we look forward to additional feedback on this TPL tool. Now, next slide, please. So in addition to the utility grid version of TPL that was presented in the last slide, there are a number of other markets that are under consideration for the TPL tool. And so here we identify a number of the powering the blue economy applications, or PBE applications, that the TPL tool is being provided. And so those three markets that are being considered are the isolated community scale microgrid, the ocean observation market, and the wave-powered desalination systems market. And so you can see the graphics for those three new PBE markets towards the bottom of the slide. But the key note is that as you look to a new market for the TPL assessment, there are some requirements and steps that need to be taken. And so first off, the stakeholders in these different PBE markets may be slightly different. And so as a very first step, what we do is we work to identify the new stakeholders for these individual markets while also looking at what systems and subsystems and again, stakeholders remain from the previous relevant TPLs. And then as we look to identify the requirements that are novel to the target application, be it the remote island community micro, thank you, the ocean ops or the wave power desal. And then once we have a sense of these new requirements, we go out with a suite of stakeholder surveys and look to understand the stakeholders in these unique markets and what their needs are. And so from those stakeholder surveys, we look to reword the questions and the scoring guidance and instructions to reflect this new application. If there are areas that are not covered, we look to develop new questions, guidance, and instructions. And then from these surveys and the adaptations that I've mentioned, we adjust the weights in our calculation based on the stakeholder feedback, solicit additional feedback, and iterate. And so if any of you are interested in these markets besides the utility scale, I'd encourage you to reach out. And I think Joachim will talk a little bit more about opportunities with the Teamer network. And so next slide, please. In addition to the work in the wave sector, we've also made significant progress on adapting the TPL to current energy converters or KECs. And similarly, the KEC markets have identified specific stakeholders, whether they be device developers and operators, current energy converter specific component manufacturers and suppliers, and site-specific environmental and marine spatial planning stakeholders. And so what we did is looked at all of the different considerations of the current resources. And those three main current resources would be ocean currents, tidal currents, and river currents. And what you can see here is a Venn diagram of the similarities and differences between those three different resources. And so while many of the considerations are common to all three resources, I believe you'll see that there are sufficient differences that justify a distinct assessment tool for each resource. And so that's what the team has done, is to develop a TPL assessment tool for the tidal resource, the river resource, and the ocean resource. And so for anyone interested in some of the current energy converter space applications, obviously reach out to us and we'll be happy to explore more and share more. Next slide, please. Now, Thomas mentioned in his slide 28 about TRIZ, which is the acronym that relates to the theory of innovative problem solving that was developed by a Russian expert, Solomatov, in the late 1990s. And so he came up with a theory for an ideal system, and it's a paradigm that's used to assess multifaceted aspects of performance over multiple questions. And so on the left, you see that there's a concept that this ideal power takeoff is a system that for no added cost or complexity provides the most efficient power conversion. And on the right side, you'll see a number of examples that must be considered as you consider developing such a power takeoff system. And now these three examples are provided, but those three dots are really meant to remind everyone that there's only a few examples, and there are many, many more examples of the trade-offs and operational constraints that you have to consider as you try to develop such an ideal power takeoff system. Next slide, please. Oh, sorry, Ryan, I didn't realize it was on a timer. Apologies. Thank you. And so the last slide I just wanted to share, and I won't quote them, but I do want to give you some insights into them, are testimonials from wave energy developers around the globe who have utilized the TPL and found it to be a valuable tool. And this tool is relevant at multiple different TRL levels. And so it's certainly valuable at low TRL as you're looking to develop and implement a technology and grow it. But it can also be super valuable at higher TRLs to make sure that you haven't missed anything as you approach fully commercial. And so on the left, you can see CalWave, which is a wave developer based out of the University of California, Berkeley. I'm proud as a Cal alumni that these guys came out of my own university, working with similar professors and similar facilities that I worked with myself. They've had a very recent deployment at the Scripps Institute of Oceanography, excuse me, and they're preparing for a major deployment at the PacWave Test Center off the coast of Oregon. They are a near-surface, semi-submerged point absorber, and you can see their device on the left. In the middle is Core Power, a Swedish company with a project ongoing off of the west coast of Portugal. They are a surface-mounted point absorber, and they have significant projects under development globally. But again, their main project is currently active off the coast of Portugal. And on the right, you can see the M4 device, an Australian company. They are an attenuator type wave energy converter, and they are currently deploying a project in King George's Sound in Australia. So I hope these comments have been helpful. And again, I appreciate the opportunity to present to all of you today. Thank you very much.
Thanks a lot, Jonathan. Next slide, please. Yeah, thank you. Okay. So we just touched the diversity of users across the TRLs. And now there's also diversity for technology performance level use across the users and the beneficiaries. So these are listed here, and pretty much most of those cases have already been used and implemented. So of course the developer, and that's really the main idea of TPL, to provide a tool to the industry, to the developer, to optimize their technology development trajectory, to come to the goal quicker, and most importantly, not to encounter risks that are so high that the combination of technical risks, corporate risks, and everything that influences this lead maybe to a failure of the company and or the technology. So for the developers, of course, but also possibly for investors, these could be private investors or public funders, to make decisions how far technology is still to go to come to market entry. And there have been numerous situations, and people in the industry will know these very well, where maybe an investor would say, okay, to a company that it's TRL 7 would be very interested in investing into it, because it appears that there's not much path to go to market entry, whereby a different company or technology that's at, I should say technology that's at TRL 3 or 4 is regarded as, you know, that's nice work, come back in a few years and then we can talk seriously. At the same time, if the promise of the technology is higher, the remaining path to market entry might be shorter, which means that this technology under development has a higher value because it needs less investment to come to market. And so this is one aspect we'd like to highlight about the value of technology and its investability by any sorts of funding support or investment support. Then in those processes of funding allocation, more precisely, for example, in a prize, there are judges that need to make decisions, and this tool may be supportive of making these decisions along with many other criteria that are not technology-based, but maybe based on the purposes and the goals of a prize, like we have it here. Reviewers in funding applications and decision-making, maybe down-selecting. We've done both of this, particularly in a prize, quite extensively before, in a prize in 2015-16. And a very nice observation was at that time that even though the tool is clearly subjective, because it depends on who's doing it, it's clearly not precise. In the nature of that there's no precise formula behind it, but it tries to be holistic and not to, so kind of the goal is really robust against failure. And at the same time, the scoring results across several different assessors, over 90 concepts that were assessed in the Wave Energy Prize, showed a very strong consistency. So once the average score of one assessor was used to normalize their scores, so their harshness or their, in a way, a big element of their subjectiveness was taken out, the ranking across all evaluations was very consistent across the different assessors. So it appears that it does lend itself to make reliable or useful relative comparisons. Yeah, maybe that's enough for what the use cases are. And across those different generations of tools, when we try and sum up across all these users, some of them we are very well aware of and have collaborated with them. Many of them we've done ourselves. Others we have supported industry players who scanned many technologies to use the methodology. Some have adapted it to their own needs. Many international projects have used them to down select ideas within the projects, and we've been in support of that. And some of the assessments have been very, very, time and intensive in terms of the engagement and the time spent on it. And some have been very light and fast, down to hours. So the range is from hours to days to weeks, maybe across a few months, depending on availability of the involved people. And if we add these up, we can definitely say that more than 1,000 applications have been are known across those different user types, and well over 200 technology concepts have been subjected to the tool. This may not be as apparent because, of course, these results and the efforts are often intended to be confidential to the user. Even when it's done as a service, there's confidentiality to the client. Yeah, and very important that this service is now, it has been, but it will be much more prominent and more intensively made available to be used through the funding scheme TIMA. And the nice thing about TIMA is that it's internationally accessible, because the applicant can come from anywhere and will benefit from the service done on their technology. However, the service is performed within the US, so the money stays within the country, which makes the benefit available to everybody globally. Yeah, so much on this slide. Next slide, please. Now, 2 slides are about the methodology steps. And maybe just let's click twice more so we have the whole slide together. Thank you. So the 3 phases are that we first of all need to understand what the technology is, and as far as this is possible, in great detail. And this, the terminology we used so far was technology submission request. So the evaluation of the technology starts with getting information about the technology and having a dialogue with the developer or whoever the information provider is and the assessing entity, if they're not the same, to fully understand what the technology is. And the point here is the difference between assessment and describing boils down to a very fundamental consideration of TPL, is that we want to separate the steps of describing the technology and assessing the technology. So what we do not want is to say, hey, tell us how good it is. And then we get the result of the assessment without really doing an assessment and without really looking at the merits and the details of the technology. So we have the description of the technology on the left, and we have the assessment or evaluation through the tool that has been described. And the result will be 2 things. It will be, that's okay, we can stay on that slide. On this one, the next one will be that we have a result of the assessment that's being described, but the conclusions out of this is also a provision of a technology development plan. So in overall, we want to kind of describe these 3 steps and the tool of TPL as inherent to a technology evaluation and development advisory. And this is also the terminology which we're going to use in the future. And here you see the same 3 steps. The different scenarios, who's involved, and what there is to be done, but I think we have covered that. Next slide, please. Yeah, so back to the price, more closely to the price. So like this webinar, the 3rd of a series On TPL, we've provided other webinars, one on wave energy in general, one on innovation methodologies, and one on distributed embedded energy conversion technology. And you have all of these available to view. And also, of course, in this phase, again, like before, you have mentorship on innovation methods and technology assessment by our two expert companies, Wave Venture and Ramble. And on HeroX and in the rules document, you'll find further support in guiding you through the price. Next slide, please. Okay, and maybe just here another reminder to stay close to the rules document. And I think here we are at the end, and we'll be open for questions. Yes. Yeah, maybe we can stop sharing and bring all the speakers back on to the camera. And we have questions.
There was one in the chat, Joachim. I don't know if you saw that. It relates to how to score certain things.
Thomas,
Yes.
you want to take that? Yeah.
Yes, sure. Andy asks, in assessment areas where available information is limited, would you recommend going with a conservative estimate, assuming difficulties in future development, or with an optimistic approach, assuming challenges can be overcome with appropriate levels of R&D, or both, and output a range of values with an associated commentary? I think, I don't know, my take is that, Andy, your the last thing that you mentioned is probably the best. You explain the uncertainty and provide a commentary on, what are the challenges and what is possible with current technologies, what is not possible, and what you hope to achieve. So I think a clear description of the uncertainty will be the best approach, I think. Maybe someone else have something to add.
Sounds good to me.
We have another one in the Q&A regarding mechanical fluid oscillatory input to electric is the focus. Is it, if the assumption is true, then the mechanism of wave force conversion to mechanical fluid is not required. Is that true? So the InDEEP focus is on mechanical fluid to electrical subsystem. I assume you can see that in the Q&A. Maybe Thomas or Joachim, that's the question for you too.
Correct. The initial power conversion step is not required to be even understood or considered in this price. That's why we have given a range, a very wide and inviting range of key mechanical physical quantities and ranges to be able to work with. However, if a competitor has a mechanism for the DECTEC metamaterial that requires a different input, we would like to see how this input comes about, or even if that input sort of conversion from hydrodynamic to mechanical has maybe, let's say, non-obvious mechanisms, for example, torsion galloping of a elastic structure, and the oscillation is used for that, things like this. It would be good to display that and not just to work with 100 hertz as an input, and it is not explained how the input of the 100 hertz is delivered by the waves. Is that clear? Okay. Seems clear. Any additions from anybody?
Yeah, it looks like Paul came back with the combination of parameters, 3 hertz and 1 meter amplitude might not be part of a wave. So I don't exactly know how you want to manage that.
I
I
don't
don't know.
see that. Oh yeah, wait, in open questions,
DNA.
combination of parameters.
Joachim, I'll chime in if it's of any
Yeah,
use.
please, yeah. Okay.
Yeah, I'll just simply say to the contestants, for my 2 cents, the deck itself, like the individual energy transducer, is not a wave energy converter. And when you combine them together to form that metamaterial that Thomas spoke of, that's also not a wave energy converter. So the inputs don't have to correspond or even correlate to a wave energy source. We've just given you a bound with which we anticipate to be of particular interest for metamaterials to be used as ocean wave energy converters when you combine them together. So I think sort of focusing on what an ocean wave would be as an input for a metamaterial or a deck is sort of missing the mark a little bit to some degree with the prize. I hope that helped everyone. Joachim, I'm sorry if I overstepped my bounds there.
No, not at all. This is teamwork. And I think we are in alignment because that's why we gave this very wide range and inviting range of values for the different physical parameters. Even at a range that doesn't appear obvious that waves can deliver that, because we are aware of some mechanisms that can be used to deliver those frequencies and amplitudes. Yeah.
Yeah, cool. And in fact, my last thought is, if anyone comes up with a clever way to step up or step down different energy inputs from an individual deck to a deck metamaterial, that would be exciting. Just sort of a personal plug there.
Yeah, and maybe I just want to add something more. I mean, where we see many of the decks and the technologies that have been proposed in the prize and outside of the prize do naturally not have the power density or also the frequency range that is originally desired by wave mechanics. So there's a lot of innovation in this step that we just talked about, the hydrodynamic to input of the wave energy converter, and just encouraged by Blake, if you have some ideas there, share them. But also between the wave energy system structure, the metamaterial, and then from the metamaterial to the deck, which is fully in scope of the wave of this prize. And there is a lot of innovation opportunity in there. I just want to, point that out. And I also believe that the prize will deliver some novelty in the combination of a deck to a deck metamaterial, how things are embedded, and how transfer functions can be realized. Also speaking those quantities that we talked about. Thanks.
I wish to take Nicole's question if there are no other questions from the attendees.
No, but I don't see any. The only other question was answered offline, by Amber, I believe. So you're good to go, Thomas.
Okay. So Ryan, can we go to slide 22?
Yeah, give me a minute to pull that up.
Yeah. So Nicole's question is, why are VEC failure rates so much higher? Is it related to operating in the marine ocean environment? Do the wind turbine failure rates represent only offshore, only onshore, or both types of turbines? So thanks for bringing this up, Nicole. I mean, I should have added, I should have mentioned this. So the wind turbine failure rates, which are shown on the right-hand side, the red bar chart on the right, that's a little outdated. If you look at the reference that I took it from, it was published in 2007, and it's for land-based wind turbines, and they're all 1 megawatt turbines. But I think to answer the first part of your question, my point is the VEC components are much more complicated. So we have an oscillatory excitation, and sometimes it gets very extreme. So there are end stops. We need to convert oscillatory to translatory motion sometimes, and in addition, your whole thing is getting rocked back and forth all the time. So it's more complicated, and it is in a much more hostile environment. And I believe that is why it's we see very high failure rates for the VEC systems. So I will let anyone else chime in if they have some things to add.
I know in my experience, Thomas, Nicole, that most WEC failures don't occur necessarily because people miscalculate how the device is going to convert ocean wave energy into electricity. Like the underlying physics, more often than not, is understood and implemented correctly. But it's what I would define as nonlinear things that people sort of miss that cause the failure. So for instance, snatch loading on mooring lines, or even just the caissons of gravity anchors tend to fail. There's been several instances where there's been cavitation affecting the hydraulic lines that were unexpected in device designs. So yeah, it's just like the devil's in the details, maybe if I could use a cliche that causes a lot of the WEC failures. And the environment, as Thomas mentioned, is relentless. It never stops. It just keeps on going and going and going. So
Well,
might be
I
old.
mean, I can kind of leverage off what Blake just said from the current energy converter space. Everyone knows there's turbulence, but in the tidal energy space, the turbulence intensity was actually underestimated. Similarly, everyone knows there's a shear profile, but the shear profile was incorrectly characterized. And so I think what Blake said is right, is that people understood the physics, but they maybe didn't understand this specific, for example, turbulence or shear profile in the environment. So I hope that's a useful sort of analog.
Yeah, and I mean, this leads on to the next thought, which is the maturity of the technologies. Of course, wind is decades maturer. And this also feeds into the understanding of the working environment, what you just mentioned, Jonathan and Blake. So, even for a new prototype with a new subsystems in wind, at least the operational environment is well understood, including standards and all sorts of support.
Yeah, I mean, since you plugged it, Joachim, I'll just share with everyone that the international standards community is preparing to write a new standards on turbulence characterization. And that touches on exactly what I mentioned, where people were underrepresenting or underestimating the turbulence in the environment. And so the international community has come together to agree on a new standard for how to accurately characterize turbulence in the marine environment, such that it can be used to ensure that load predictions are more accurate and more likely to prevent premature failure of devices in the ocean environment. So thank you for that, Joachim. I appreciate that.
Sure. Okay, I believe we are on time, and it looks like everybody's happy. So maybe let's close it here. And as usual, if anybody who missed the presentation today, you can get the slides and you can get the recording. Thank you.
Thank you all for inviting me. I
all.
appreciate it.